Okay, guys. Well, today we'll go through chapter 9 and 10. As you can see, we'll talk about the atmosphere in chapter 9, and then chapter 10 will go for the air, for the air pollution and the effect of the air pollution on the environment. So we took the tower, contamination, and pollution. Now in this chapter, we'll take the beginning of the air, what's really air, what those major pollutants, and then we'll take in very specific problems with the air pollution and the Clean Air Act as well. So first of all, we define, as I said, the atmosphere. So the first thing here we do, we define the atmosphere. Well, it turns out the atmosphere consists of gas molecules, mostly nitrogen, oxygen, and other traces of gases. And you will see later on the altitude of this atmosphere made of three layers. And in those gases, some of them found naturally, like nitrogen, oxygen. Those are in the air; they're naturally there. But then some of them those gases are human-made, such as methane, carbon dioxide, then the halogenated chlorofluoro organic compounds. All those gases and those things inside the atmosphere. Those except for nitrogen, for air, which is made of nitrogen and oxygen. 70% of the air is nitrogen, and 24-something% is oxygen, and the rest is the gases: CO2, carbon dioxide, inert gases, and this moisture, and the hydrochloro organic compound. So minute particles, very small particles, and liquid droplets, collectively called aerosols, also are suspended in the air. We'll keep them. This is the clouds, which the clouds are made of what? Of thick, of H2O itself. H2O, when its temperature is suitable, then can collect itself as a cloud. Correct? The atmosphere has 4 distinct zones. One of them, ours at the bottom, which is close to us, contrasting temperatures due to difference in absorption of solar energy. The layer closest to the Earth, called troposphere, and experience everyday changes in temperature and rain, precipitation. So we call it the weather. So here's just the idea. You don't have to memorize this, but here the idea is, the bottom here, all the way the bottom here is, maybe I can take this one here. Let's copy it, and then I hope it will copy. I'm just copying this so we can make it bigger. Here it is. In the PowerPoint, you can't see it very well. It is. So you can see layout. Okay, now we can make it bigger. I think you can see it much better now. As you can see here, the close to the Earth, where the clouds are and everything, you can see the picture of an airplane there. That's a troposphere. Okay, that's what we can really see in our eyes when we go to the skies. We call it in the sky itself. That's what the troposphere. That's the bottom one. And this red one here, this circulation of the air itself. So that's the circulation of air moving of the air here. See, circulate here. It is. That's what's helping this circulation is the wind. The wind is helping circulating the content, whatever inside the air. So the first one here is that's what we can see, that's troposphere. Then you go higher, then, as I said, here you can find H2O. Here you can find CO2. This is H2O. You know H2O is tabor, correct? And carbon dioxide, CO2. And you can get us this halogenated, let me write it here. They call it CFC. This is fluorinated hydrocarbons, carbon. So fluorinated, C for chlorinated, F for fluorinated carbons. Those are chemicals that's used as in the aerosols to keep up the blood, to keep up the pressure high so the aerosol can come up of the bottles. Yeah, so this is what you can find in this area here, beside the air, of course. Air, which is air nitrogen plus oxygen plus the group number 8, which is, if you look at the group number 8, inert gases, noble gases, inert gases such as helium and argon. Helium and argon. So all those are found in the first one, in the troposphere. Okay, you go higher, then this is disappearing. They are not there with altitude. Are you following me here? Then only you have what? Ozone only. So they are not there. Not there. Only ozone layer there. The second one, the stratosphere. That's higher. And then you can see here in miles, the altitude in miles here, and the altitude in kilometer here. Somebody will tell me. Somebody drove in a car in Europe, or somebody? How much is the mile kilometer? How much? Roughly.
15, I don't know.
From there, so 50 is corresponding to what? To 86. Correct?
Yeah, that's the thing.
How much is it? 1 mile is Gesundheit. 2.26. 2.26. Yeah, about 2.26 kilometers. So the mile is bigger than the kilometer. So anyway, but you go higher than this, that you get the stratosphere. They have only ozone, only. Then you go higher, then no ozone, no nothing. Now here we are talking about what? Especially the last one, the thermosphere. That's like a vacuum. Correct? You know what vacuum means? Somebody will tell me what vacuum means? Vacuum means you have no air, no nothing. You cannot live there. There's no air, no tabor, no nothing. So with this vacuum, you have to have special gadget to live, like like you're on the space shuttle, whatever. But that's the highest one, thermosphere. So mesosphere, you not get any of those gases, no ozone there. Okay, and but the air is enough to be pushed sometimes with the wind. With the heat, can be circulate through all this. But air can go, because air is the smallest particle from all those particles you can see here. Correct? You don't have to memorize this, but at least you have to know that the temperature is very, very important factor. So here in this, let me just put this one here, different color, not blue, but maybe. Here it is. This is your 0 degrees. This is your 0 degrees Celsius. 0 degrees Celsius is corresponding to what? 32 degrees Fahrenheit. Everybody agrees? 32 Fahrenheit is equal to 0 degrees. So this 0 here. So if you go to this area, you can see temperature is being very cold, minus 100 centigrade Celsius. Nobody can live. I don't think so. Any living creature can live this type of temperatures. That's frozen to death, we call it. So really frozen to death. You cannot live there. We can live up to minus 60, minus 70. That's in the North Pole temperatures, around that temperature, minus 60 to minus 70. But then if you go beyond this, that's very difficult to live. So this area here, you can see all this area here is very, hold on here. This area here, all this very low temperature. This area here is a little bit higher in temperature. As you can see, the whole Earth is a sphere. It's not rectangular or a cube. It's a sphere. So it's like the area it's exposed to the sun is very hot or very warm or warm, depending on the location. And the area is far away from the sun will be cold. So you can see that those temperatures here taken from the area, the sun is here. The sun is here, okay? So this area will be warm, while the other area is very cold. And if the rotation of the Earth the other way, you'll see that those are exchanged. Those positions are exchanged, correct? So that's just an idea. You don't have to memorize it. I did not ask you any question about this, and I don't want to memorize, but at least you know that those are type of the whole thing. And the most important or striking feature is our troposphere. That's what the problems are. All the problems of air pollution are coming here, correct? And there's factories are dumping SO2, as you will see. That will give you sulfuric acid to act with the moisture. There we have said H2O. Those two give you sulfuric acid. The nitrous oxide, the nitrogen dioxide, will give you H2O, nitric acid. Those both sulfuric acid, nitric acid, those are the major component of acid rain. Acid rain destroys the soils, kills the plants, and kill all the living creatures in the forest, and can affect humans as well negatively. So acid rain is not a joke. So it's really affecting the environment very, very in a very negative way. So as I said, I'm taking this one out just for ourselves, so to know about those four areas. And the most important for us is our area, the troposphere, which is all the problems are there in that area. You go higher, 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 there's no, we have no control on it. Those are, they have, what they call it, they have no gases, no pollution, no nothing. You just, circulation of the air can go up and down because of the temperature, correct? And the air is, as I said, the tiny molecules of all with the H2O. Air is just nitrogen, oxygen. So let me take this one here out and go back to the so atmosphere captures energy selectively. Yeah. So what's happened is those chemicals, you have them there, and the clouds of the moisture of H2O, they have and CO2, for example, all those gases you can see, they have the feature, the physical property to absorb energy in them. So they absorb energy here. The sun supplies with a lot of the Earth with a lot of heat, energy here, and then those gases you have seen as actually in our troposphere, our skies or our sky. That's where there is absorbed this energy is there, and you will see 1/4 of this energy coming from the sun reflected by the clouds and atmospheric gases. 1/4 absorbed by those gases, correct? As we said, bunch of gases I put for you, just to name a few here. But I put you almost every pollutant there, and half of incoming solar radiation in oscillation reaches the Earth's surface. We not get 100% of the energy of the whole thing, because some of the heat is absorbed by those gases, and some of the heat is absorbed by the clouds, and some of H2O, and some of it is just absorbed by the reflected away, correct, back to the higher stratosphere and the higher one, the mesosphere, to the higher altitudes. So, what is greenhouse effect? Well, greenhouse effect, as I said, we mentioned a couple, just 1 minute ago, is the ability of the gases found in the air to absorb energy and keep it and maintain it there, and it's not reflecting it anywhere, absorbing it, and therefore it cannot go there.
I'm sorry.
So, the greenhouse effect is a common term to describe the capture of energy by gases in the atmosphere. That's what we said. And the CO2, if we have halogenated, fluorinated hydrocarbons, and you have what else? Air is a small nitrogen atom, will not be able to absorb that much energy. But CO2, organic, chlorinated, fluorinated hydrocarbons, those the major one will absorb a lot of energy here, and carbon dioxide as well. So they will not let those heat escape. So the heat will come in the sun, will be absorbed, and whatever we are manufacturing, we are reducing heat as well, and it will be what this energy we are producing from our power plant, nuclear plant, whatever factory we are using. So this heat will go up, and then cannot go through because it will be absorbed by CO2. So CO2 is like an isolator for the heat. That's what is really global warming is all about. That's what global warming is all about. So the CO2 and all those organic halogenated, fluorinated compound, those will not allow the heat to escape out to stratosphere, mesosphere, to the higher altitude. So they will end up in the vacuum somewhere in outer space. But that's not happening. They will keep the heat and the energy there, and that's what we call greenhouse effect. And as I said, it's really affecting the temperature of the whole Earth, correct? Mm-hmm. So, climate changes over time, that's really true. Climate changes over time, yes, that's really true, depending on all the circumstances is dealing with the climate. How stable is climate? Well, it depends upon the time frame you consider. Over centuries, the climate shifts somewhat, but usually we expect little change on the scale of a human lifetime. So it takes millions of years to see the change, millions of years, not 100 or 1,000, millions of years to see really change. It's a very slow process, but it's still there. There is evidence for that. It's there. The climate does change. The question now whether that is reasonable expectation, I think yes. If climate does shift, how fast might change, and what will those changes mean for the environmental system we depend on? As I said, climate changes takes millions of years. It's not a matter of 100 years, 200 years. Takes thousands and millions of years to see really a change. It's a very, very slow process, but it's still there. And the global warming, one of the expectation that those gases we are dumping inside the air, inside our troposphere altitude, that's what they're keeping absorbing all the heat coming from the sun and all the heat we are generating there. So that will cause the whole thing. And what the second evidence we can see that's really we have global warming? Somebody will tell me. I did not put this one in a quiz, but might be in the final exam. What evidence that we have global warming.
Besides the climate?
Correct. What's happened to the North Pole and the South Pole? Yeah, that's very obvious. That's whatever now you can see what's happening to all these icebergs in the North Pole, South Pole area. They are shrinking per time. I mean, it takes time, but you can see the difference. I mean, you can see the difference. But say 20, 30, or 50 years, you can see there is something happening. There is something happening. That's you see this is shrinking. The icebergs are shrinking in size. But it takes, as I said, thousands and millions of years to see a change. If we can see a quick change, then what will happen? Those icebergs will melt, and you have flood, and cities, and maybe continents will disappear. Correct? Continent, not only cities or small tiny places, but all continent might disappear. And that's not happening. I mean, hundreds or thousands. It takes time. It takes very time. But the time is coming. The time is coming, and you can see that's really evidence that the time is coming. And here is tell you what's the causes. This climate can happen naturally because of the rotation, spinning of the Earth around itself. And you can see here, there's 2 degrees, 22 degrees over its axis, and 24 degrees over its axis, and that's causes the climate naturally. That's without our intervention. But we can't change the climate by dumping a lot of pollutants inside our troposphere layer. Okay, so that's a spinning of the Earth around its axis from like 2 degrees, from 22 to 24 degrees, can cause climate changes, because that's spinning a rotation around itself, and then it rotates with this rotation around the sun. That will affect the whole climate. But this is happening in 11-year cycle. So in the sun intensity. So how do you know the climate is changing faster than usual? That was my question, correct? Mm-hmm. So many scientists consider the anthropogenic human-caused global climate change to be the most important environmental issue of our time. And that's really true. We are contributing for the change of climate. We are contributing for the pollution of the air and water and the whole environment as such. So the human activities are really increasing the atmospheric CO2. Okay, and you can see in the area there's a lot of earthquake and volcanoes. I think if you look by now over the say 1,000 years, you'll not see that much of volcanoes recorded 1,000 years back. Earthquake and volcanoes are recorded like in the last say 1,000 years or 500 years from now. 500 years you have a lot of volcanoes and earthquake all over the earth, and it means for us something happened to the whole earth and the whole climate in the earth, affecting these earthquakes and volcanoes. And the carbon dioxide level increasing about 0.5% per year since 1958. The skipping curve shows that CO2 concentration have risen from 315 parts per million in 1958 to 339 parts per million in 2012. So within a couple of years, you can see in 58 to 12, that's about maybe 40, maybe 60 years or so, you will see that a couple of parts per million is increased from 315 to 393. So that's not that much. Part per million means part of the million concentration. That's not that much, but still in the scale for the environment, global warming, that has a big effect. Scientific consensus is clear As I said, there is among the sciences there is no difference that there is a global warming, and we as a human are contributing to it, and we are polluting our air as well. Climate scientists worldwide have collaborated in collecting and sharing data in programming models to describe how the climate system works. Evidence shows minor differences among models, but there is no disagreement. All of us agree there is a global warming. There is a global warming there, and there is a lot of air contamination, especially in the developed countries. If you go and look at some cities in India and China, in one day or sometimes in a year or a couple of days in a year, you cannot even see all this smog, all this brownish gases, all this stuff here, and you can't even breathe. And even you cannot drive a car very well. It looks in the middle of the day, like in the night, everything is dark. You cannot see. Sun cannot be even seen because of the pollution of the air. Especially in India and China, they are heavily involved in industry without regulation most of the time, and that's what leads to this pollution of the air. Evidence shows unequivocally that climate is changing, and the global average is a warming because of increased attention of energy in the lower atmosphere, in our stratosphere. That's where all those gases are carbon dioxide mostly, and the CV, chlorinated, fluorinated hydrocarbons. They are absorbing this energy there. They retain this energy. What is IPCC? Well, this is Intergovernmental Panel on Climate Change. This is a panel there to provide for the public and provide all this data. So, and this for the public and for the whole world. They have about 130 countries are involved in this, and they have to see that there is an evidence of human involvement in this global warming, in this climate change. In 2007, the IPCC issued its fourth assessment report. The conclusion is 90% certainty that observed climate change is caused by human activities, and that's really always true. And subsequent reports raised the certainty to 99%. The involvement of a human is not 99. It's really 100%. That's really what's happened, because nature, if you look at the whole picture, nature is always correcting itself if there's no intervention from humans. Are you following me here? If the nature kept by itself, it will correct itself naturally. But then the involvement of a human inside all this stuff, inside pollution of clean tap water, and then clean fresh tap water in the rivers, lakes, and ponds, and the same thing happened to the air. So that's lead to this climate change or climate destruction. I mean, you get the climate but it's a very slow process. As I said, it's very, very slow process. If we have really cleaned the whole thing, nature the ability has to correct itself by itself without intervention. Main greenhouse gases, as I said, methane, that's natural gas, carbon dioxide, chlorinated, fluorinated hydrocarbons. This is nitrous oxide. What's the name of this, the commercial name of this? N2O. Somebody will tell me?
N2O.
This one here. That's methane, correct? Natural gas. Methane, correct? And this is carbon dioxide. You know that. Carbon dioxide. This is nitrous oxide. But what's the commercial name for it? Nitrous oxide. What's that? When you go to the dentist, they put sometimes gas on this.
Oh.
What's that? That's so-called laughing gas.
Mm-hmm.
If you have this one in your, taking this one too much of it, you start like panicking and laughing like crazy. People think that you are out of mind. Yeah, that's a laughing gas. So the commercial name of it, you hear about laughing gas, that's really making you laughing like crazy, and then people think that you are out of mind. So something happened to your brain. So but anyway, so those, you don't have to memorize this, but at least you'll have the opportunity whenever you see this, you remember the laughing gas. A long time, but they stopped. Long time the dentists were using it. But then you have to ease the pain, correct? But now they have much more better drug than this laughing, because then the patient starts laughing like crazy, and it looks very funny. Yeah, so it's no longer used, but long time was used in the dentist's office. Anyway, so what consequences do we see? Well, with all this pollution here, you can see half a degree. That's a half degree increase. So we have 0.6 or half degree Celsius, which is here, which is about 1 degree Fahrenheit was increased through the years. So in the last 2 years, 2,000 years. So as I said, the change cannot be seen at once. It takes thousands and millions of years to see real change, as you can see here. Global sea level has risen approximately 2 centimeters, 8 inches in the past century. Permafrost is melting. Houses, roads, pipelines, sewer systems, transmission line are being damaged. And you will see later on some statues, very nice artwork are being destroyed because of this erosion of those pollution in the air. So, and Arctic Sea is ice is only half as thick now as it was 30 years ago, and Antarctic ice shelves are breaking up. That's what I told. That's an evidence that there is evidence that you can see the climate is changing. It's a slow process, but it's changing. Evidence of this, well, beside this, you can see droughts everywhere. I mean, especially in area where the precipitation of rain is very least. North Africa, for example, in Tibet area, Mongolia area, you can see drought all over the places. So that's an evidence that something happened and something happening. So this retaining of the heat or the energy here by those gases will raise the temperature. Will raise the temperature up. When the temperature is up, then whatever is H2O you have, and you can expect to precipitate, the H2O evaporates. Instead of precipitating, it's evaporating because of the heat. It's not precipitating, correct? Because of the heat and the wind. Droughts are becoming more frequent and widespread. Plants and animals are breeding earlier or extending their range into few places. Coral reefs worldwide are bleaching, losing key allergies. So climate change will cost far more than climate protection. As I said, climate change is costs more than the climate protection. So financial cost of drought, damage to infrastructure, loss of biological productivity, and loss of water supplies caused by changes in climate will be enormous, will be a lot. I mean, it's just, cheaper than to protect, to protect the climate than to do all this clean up and all this repair for all this damages that the pollutants are making. Envisioning solutions. Well, there's a lot of envisioning solutions, as you can see. There's a lot of now. If you that's not in the PowerPoint, but just to let you know, the power plant, and I think to some extent I don't know about nuclear plants, but the electrical power plants, they have special filters on these towers, stacked towers. When they dump anything inside the air, it has to go to special filters, and that's not in the PowerPoint. But those filters are really helping to contain all the solids, particles, and all the harmful chloro and fluorohydrogenated chlorofluoro hydrocarbons. Those can be trapped before they are dumped by mistake or anything to the air. So there are enough filters in those electrical generating power. So former President Bill Clinton has argued that combating climate change does not have to mean economic hardship. Matter of fact, if you start controlling the climate pollutants, then that can bring you a lot of money and bring you a lot of jobs for people working in that area. So the Paris Agreement establishes new goals. Well, this is I mean, one very important goals. That's to cut off the carbon emission, and that's what they introduced that time, the catalytic converter, to reduce all the sulfur and nitrogen and carbon-based gases. So, as I said, the average temperature increased to 1.5, below 1.5, so it's decreased. So it's increased. Its average global increased to about 1.5. Zero carbon emission is global goals. That's one of the agreement of the Paris Agreement. So that's a big conference there, and they reduced the mandate is to reduce carbon emission to zero, and not only carbon. You have sulfur, you have nitrogen coming on those burning gasoline-based cars and then tractors and even diesels. So each participating country establishes voluntarily emissions reduction goals. Climate finance necessary advanced economies agreed to strive towards donations of 100 billion per year to a green carbon fund. Means zero carbon. We have many drawdown options right now. As alternative approach is wedge analysis. What means wedge? You have a big problem. So how you solve a big problem? You have a lot of pollution there. So how you solve it? Break it in small pieces. You cannot combat the whole thing, but the idea is take it piece by piece. First, I'll concentrate myself on the chlorinated hydrocarbons. Then I'll concentrate myself on the methane, then carbon dioxide. And so I cut the pollution problems into small pieces so I have more control. But if you can come at once, that will cost you a lot of money and a lot of effort to do that. So breaking, even in the real life, if you have a problem in a factory or anything, you'll start with breaking the problems in small pieces. And then when you have these small pieces, then you can correct or can work on one piece by piece until you eliminate the whole source of the pollution. Each one of these pieces starts small, but then the impact will grow over time, producing a larger wedge-like impact in 50 years or 100 years from now. And this is just an example of this cutting a problem in small pieces. Bacala and the Socolo paper, those two scientists, they have published their finding, describe 14 wedges breaking down for a problem. Each represent 1 gigaton, 1 billion ton of carbon emission avoided in 2058. So by 2058, we should really almost eliminating carbon emission. Well, that's the goal I think can be adhered and can be followed in the developed countries, but in the developing countries, as I mentioned, especially India, China, those are the most countries that's really participating in air and then the tower pollution because of the factories there they are producing, but the regulation is not that tough. It's not that tough enough to really control the pollution itself. Carbon capture stores CO2, but it is expensive. It is possible, though expensive. It is possible to store CO2 by injecting it in deep geologic formation. So what's happened is, I think Norway is doing this. They are digging a lot of big holes inside the ground and fill it with a lot of concrete and making like small manufactured reservoir. And this, they are dumping whatever CO2 they have, they dump it inside. So they tell them the factories, if you have CO2, just bring it to us in barrels or special tanks. We are saving it inside inside those manufactured reservoir or manufactured tanks inside the soil. So, and they have it pressurized, and they can use it for future use. Where we can use CO2. So if we have captured the CO2 from the companies and the factories, and we are really having it contained inside special reservoirs, special tanks inside the soil, inside the ground, we can reuse it. But where we can use it? Inside your lab, for example. Where? Inside your kitchen. Where?
The stove?
No. Fire extinguishers. You put the fire off, that's CO2. That's CO2, you see? That's the high pressure, you can make it powder. So it is gas. It is a gas. But enough pressure, you can use it as a combat fires. And that's a very good usage of carbon dioxide. Well, you can make out of it sodas. You know, the fuzzing gas coming out of when you open the sodas, that's carbon dioxide, correct? So you can use it for the manufacture. So, going to a little bit of chapter 10, we'll talk about air pollution and health. Well, we talked about this, and the pollution comes in many forms. Smoke, haze, dust, odors, corrosive gases, noise, toxic compounds, and among our most widespread pollutants. Those are used. Pollutants may irritate our eyes, lungs, enter our bloodstream when we breathe them, and then damage nerves and brain functions. The Organization and Economic Cooperation and Development has projected by 2050, chronic exposure to pollutants will cause 3.6 million premature deaths every year. And that's really true. And as we will see in this air pollution, most of those pollutants are really manufactured by humans. And you will see mercury, one of them here, lead, and then you will see all these gases coming, carbon dioxide, sulfur dioxide, nitrogen dioxide, all those oxides will come as a pollutant. I will stop here, and then I will see you then next.